Hello and welcome to Anatomy of a ConvNet, a visual journey from simple digits to hidden deception. Convolutional neural networks, or ConvNets, are the foundation of modern computer vision. They are the systems that allow machines to classify images, power self-driving cars, and perform complex object recognition tasks that were once thought impossible for algorithms. But how exactly do these intricate mathematical structures work? And perhaps more importantly, what are their hidden limitations? Over the next few minutes, we will embark on a visual journey. We'll start by breaking down a basic ConvNet architecture used for a simple task. Then we'll scale up to a monumental deep learning system, the VGG16 architecture, to understand how feature hierarchy is built. Finally, we will shine a light into the black box to explore what these networks truly learn to see, only to reveal a startling vulnerability known as the adversarial attack. This journey will demonstrate that, while ConvNets are incredibly powerful and perform complex tasks with superhuman accuracy, their internal understanding of the world is surprisingly fragile and exploitable. Let's begin by laying the groundwork with a classic challenge. To truly understand how complex ConvNets operate, we always start with the most famous introductory problem in machine learning: classifying handwritten digits. This is the MNIST dataset. It is often referred to as the hello world of computer vision, and despite its age, it serves as the perfect foundation for building a simple convolutional model. Our dataset consists of 60,000 training images, with each image being a small 28 by 28 grayscale picture of a digit from 0 to 9. While this task seems trivial to a human, we instantly recognize that scratch as a 7 or that loop as a 0. It is computationally demanding for a machine that only sees a grid of pixel values. The task for the network is simple. Take the 28x28 pixel input and output the correct corresponding digit label, one of the 10 possible classes. The images displayed on the right demonstrate the variability in handwriting and the occasional ambiguity that the network must learn to overcome. By mastering this fundamental task, we can then confidently scale our understanding to the massively complex models used in real-world applications. Our path forward is defined by this 7-step blueprint, which outlines a simple yet powerful ConvNet tailored for the MNIST challenge. We start at step 1 with the input, a 28 by 28 by 1 tensor, representing our single grayscale image. The real magic begins in the convolutional layers. Step 2, Conv Layer 1, uses 32 filters, each 3x3 pixels, to extract basic features like edges and corners. This results in a slightly smaller 26 by 26 output, but with 32 feature maps deep. Step 3, Conv Layer 2, increases complexity by using 64 filters, allowing the network to combine the features learned in the previous layer. This results in 64 deeper feature maps. Next, at step 4, we introduce max pooling. This is a critical step for dimensionality reduction. By taking a 2x2 pool, we effectively have the spatial dimensions, bringing the tensor down to 12 by 12 by 64. This reduces computational load and helps the model generalize. After pooling, we move to step 5, flat. This takes our 3D tensor and converts it into a single vector of over 9,000 values, which is necessary to feed into the traditional neural network layers that follow. Steps 6 and 7 are the final classifiers, 2 dense layers. Layer 6 has 128 neurons for feature interpretation, and the final layer, Layer 7, has 10 neurons, 1 for each possible digit, culminating in a softmax function that provides the probability distribution for the classification. Once trained on the MNIST dataset, this simple 2-convolutional layer architecture demonstrates remarkable proficiency. The graph on the left illustrates the training process over 12 epochs. Crucially, we observe 2 important things. First, the network rapidly achieves high accuracy, exceeding 96% within the first few epochs. Second, and perhaps more importantly, the training accuracy curve and the validation accuracy curve run parallel and do not significantly diverge. This non-divergence indicates that we have successfully avoided overfitting. The network is not just memorizing the training examples, but is generalizing well to unseen data. After just 12 epochs, the network achieves an impressive overall accuracy of approximately 99%. The examples on the right further illustrate the network's prowess. These are validation examples the network has never seen before, yet it performs flawlessly, correctly identifying diverse and sometimes ambiguous handwritten characters, such as the number 9 or the 4s in the second row. This simple model confirms the fundamental power of the ConvNet architecture, even on confined problems. But now we must ask, can these core principles, convolution and pooling, be scaled to handle the visual complexity of the real world? Having mastered simple digit recognition, we now transition to the summit of visual classification, real-world photography. The core principles of convolution and pooling are fully scalable, and we move from classifying just 10 simple digits to tackling 1,000 distinct, complex photo categories. This transition brings us to the ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC, the gold standard competition in computer vision. The task here is vastly more challenging. The network must classify 1.2 million high-resolution, real-world photographs into one of 1,000 different categories, ranging from animals and vehicles to complex architectural elements and geological formations. We turn our attention specifically to VGG16, a landmark network developed by researchers at the University of Oxford's Visual Geometry Group, which won the ILSVRC in 2014. VGG16 demonstrated that deep, uniform architectures could outperform previous, more complex designs. It showed that simply adding more layers, provided they follow a consistent pattern, was a highly effective strategy for tackling the visual world's enormous complexity. The VGG16 architecture is defined by its elegant methodical structure, which relies on blocks of uniform layers repeated throughout the network. Unlike other networks that might use varying filter sizes, VGG16 uses only 3x3 convolution filters and X-max pooling layers. This consistency makes it robust and easy to analyze. The design follows a crucial pattern. As we go deeper into the network, the spatial dimensions, the height and width of the feature maps, shrink, while the depth, the number of filters, doubles. Let's trace the first half of the architecture. The input is a 224 by 224 by 3 color image. The first block uses 2 convolutional layers with 64 filters, followed by a max pooling step. This pooling halves the spatial dimensions to 112 x 112, while the depth remains at 64. The second block repeats this pattern, doubling the filter count to 128 and pooling again, resulting in a 56 x 56 x 128 output tensor. The third block further increases the complexity, using 256 filters, which brings the tensor down to 28 x 28 x 256. This progressive contraction of spatial information and expansion of feature depth allows the network to gradually shift from detecting simple local features to assembling highly abstract visual concepts. We now continue through the final stages of feature extraction and into the classification head of VGG16. Groups 4 and 5 represent the deepest convolutional sections, where the most abstract features are extracted. In Group 4, we use 3x3 convolutional layers, all employing 512 filters, reducing the spatial dimension to 14 by 14. Group 5 repeats this structure, maintaining 512 filters but pooling down to a final feature map size of 7 by 7 by 512. At this point, the output tensor, which is 7x7x512, contains 25,088 highly compressed, abstract features or learned patterns necessary for final classification. This tensor is then passed to the classification head. The first step here is flattening, converting the 3D feature map into a massive 1D vector. This vector is then fed into 2 large dense layers, each featuring 4,096 neurons. These layers act as the final decision makers, interpreting the highly compressed features to determine the category. Notably, these dense layers also incorporate a 50% dropout regularization technique, meaning half the neurons are randomly ignored during training to prevent the network from becoming overly reliant on specific features, thus ensuring better generalization. Finally, the output layer consists of 1,000 neurons, corresponding to the 1,000 possible ImageNet classes, followed by the softmax function, which yields the network's confidence scores. The sheer depth and methodical structure of VGG16 translate into truly impressive real-world performance. Despite only being trained on the ImageNet dataset, VGG16 exhibits powerful, generalized visual understanding that allows it to accurately classify images it has never encountered before. For instance, the image of the Seattle Space Needle, which VGG16 likely never saw in training, is classified as a beacon or lighthouse with high confidence. This demonstrates not just memorization, but a semantic understanding of tall, navigational structures. Similarly, it correctly identifies a common street object as a manhole cover and complex machinery on the water as a fireboat. Perhaps most impressive is its ability to categorize complex textures, such as the wall covered in used chewing gum, correctly classifying it as bubble. These examples underscore how VGG16's hierarchical structure moves beyond simple object recognition to capture general visual concepts, proving it is an exceptionally accurate and powerful model capable of classifying the vast complexity of the visual world with superhuman speed and precision. Having seen VGG16 perform flawlessly, we must now delve into the black box to answer the fundamental question: what exactly has VGG16 learned to see? The network's success is entirely dependent on the numerical matrices within its convolutional layers, the filters. By themselves, these filters are just blocks of numbers, weights that are adjusted during training. To understand their function, we utilize visualization techniques. One powerful method is to use optimization algorithms, such as gradient ascent, to generate or find an image that causes a specific filter in a given layer to achieve its absolute maximum activation or strongest response. Essentially, we are asking the filter, what image do you look for? By synthesizing this ideal image, we reveal the underlying pattern, texture, or shape that the filter has been designed to detect. This technique provides us with a visual representation of the features the network has intrinsically learned at various levels of abstraction, allowing us to map the entire hierarchy of visual understanding from simple lines to complex objects. The visualization process vividly demonstrates the core concept of ConvNets, the hierarchy of features. This slide starkly contrasts what is learned in the earliest layers versus the deepest layers. The visualizations for the early layers, such as those in Block 1 Conv2, reveal highly simple, foundational patterns. These filters are the most basic detectors, specialized in identifying oriented edges, lines angled at various degrees, or simple color gradients and solid color blobs. They form the fundamental alphabet of visual perception for the network. As we progress deeper into the architecture, however, the filters begin to synthesize these simple components. The visualizations for deeper layers, such as Block 4 Conv1, show dramatically complex, high-level textures and patterns. These filters are no longer just looking for a 45-degree line. They are looking for combinations of lines and colors that form recognizable semantic structures. We see intricate patterns resembling animal fur, the overlapping structure of reptile scales, complex knitted textures, or even detailed architectural elements. This progression is proof of hierarchical learning. The early layers extract primitive features, and the deeper layers iteratively combine these primitives to construct an internal, highly sophisticated vocabulary of complex visual knowledge. Beyond optimizing images for maximum response, a second crucial technique for deconstructing the image is visualizing the feature maps. This involves feeding a real-world image, here, a mallard duck, through the network and examining the output, the feature map, of specific filters at different layers. This technique shows us how the network is currently processing the image. Observe the early layer response from Block 1 Conv1 on the left. The feature maps are still relatively faithful to the input image, serving as basic detectors. Different filters focus on different low-level attributes. Some highlight the sharp edges that define the outline of the duck's body against the background, others accentuate the texture and movement of the water, while still others selectively respond only to the orange color of the duck's feet. Now, look at the late layer response from Block 5 Conv1 on the right. At this deep level, the filters respond to much more abstract combinations of features. The original image is barely recognizable. Instead, we see scattered, intense activations where the highly complex, learned features are present. The network is no longer concerned with simple pixels or edges, but is thinking about higher-level concepts: the specific shape of the duck's head, the pattern of its feathers, or its posture. This illustrates the progressive feature extraction that allows the network to transition from a raw grid of pixels to an abstract concept ready for final classification. Our exploration has shown that ConvNets possess a powerful, hierarchical feature learning system that appears robust and almost human-like in its capacity for generalization. We've seen it identify complex textures and unseen structures flawlessly. However, this impressive capability conceals a profound and startling vulnerability that challenges our understanding of what the network has truly learned. The network's understanding, fundamentally based on mathematics and high-dimensional geometry, is not equivalent to human semantic understanding. This distinction makes these networks susceptible to what are known as adversarial attacks. It is possible, through careful calculation, to introduce tiny, often imperceptible changes to an image, noise that a human cannot see, that will cause a state-of-the-art classifier like VGG16 to fail completely and catastrophically. This ghost in the machine raises deep questions about the security and reliability of AI systems, particularly as we integrate them into critical applications like medicine and autonomous vehicles. This visual comparison demonstrates the chilling reality of the adversarial attack. On the left, we have a perfectly clear image of a tiger. When VGG16 processes this image, it correctly identifies it as a tiger with a high confidence level of 80%. Now, consider the middle panel, the adversarial perturbation. This is not random static, but a carefully crafted layer of noise derived from analyzing the network's own weaknesses. Crucially, the pixel values of this noise are extremely small, perhaps changing the original pixel colors by only plus or minus 2 units on the full 0 to 255 scale. When we mathematically add this imperceptible noise layer to the original tiger image, we get the result on the right. To the human eye, the image on the right is absolutely identical to the original. We still see a confident tiger relaxing in the grass. However, the tiny, calculated perturbation has completely shattered the network's internal representation. VGG16's confidence in the correct class evaporates, and it produces wildly nonsensical predictions, such as scoreboard, screen, or brain coral. This stark failure confirms that the network is relying on fragile, high-dimensional patterns that differ fundamentally from the robust, semantic knowledge employed by human vision. Our visual journey through the anatomy of a ConvNet leads us to 3 central conclusions: that these systems are powerful, hierarchical, and brittle. First, we confirmed the power of hierarchical learning. ConvNets successfully build a profound understanding of the visual world by starting with simple edges in early layers and iteratively combining them into complex, abstract patterns in deeper layers. This architectural elegance is what allows them to extract meaning from pixels. Second, we validated their remarkable performance. When scaled and optimized, as demonstrated by VGG16, these architectures achieve superhuman performance on massive, complex tasks like large-scale image classification, defining the state-of-the-art in computer vision. However, the third point, the hidden flaw, is the most crucial takeaway. The existence of adversarial attacks reveals that a ConvNet's understanding is fundamentally different from our own. It is an exquisitely tuned, high-dimensional pattern matching system that can be exploited in subtle, mathematical ways that humans cannot even perceive. ConvNets remain the cornerstone of modern AI, bridging the gap between raw data and perception. But their vulnerability forces us to recognize their limitations. Understanding this internal logic and its inherent brittleness is not just an academic exercise. It is critical for designing the robust, reliable, and trustworthy AI systems that are increasingly essential in our world.